All right, welcome everyone to our second EER seminar of the 21-22 school year. I'm excited to introduce Dr. Erin Johnson. I always enjoy when the faculty who are presenting are from around here or someone who I know personally, so I get to brag up that this is a friend as well as a colleague. He is an assistant professor here at the University of Michigan in aerospace engineering, as well as a core faculty member in the EER program. His research explores the gap between well-defined coursework, or the way that we approach engineering in many courses, and the ill-defined socio-technical nature of true engineering practice. He has a BS from U of M in aerospace engineering, as well as a PhD in aeronautics and astronautics from MIT. All right, I'll let you take it away.
Sure. Thanks, Robin. Yeah, it's great to be with you all and have a chance to introduce myself or reintroduce myself. So I'm Erin Johnson. I'm an assistant professor in the aerospace engineering department. It's still a bit surreal to hear myself described as that. And so I'll be talking today about my research, which is focused on understanding the productive beginnings of engineering judgment. So I will start by giving you a little bit about my background, telling you a bit about who I am and where I come from, then give you the overarching motivation for my research, and talk about sort of the overarching research questions that I seek to address in my body of work. And then I'll talk specifically about one project that's been going on for a few years on the productive beginnings of engineering judgment. So I'll talk about this new type of problem that I developed, open-ended modeling problems. Then I'll talk about the qualitative research methods I use, and then I will get into some preliminary works, which is the development of a new theoretical framework of the productive beginnings of engineering judgment. And I will talk about both what I mean by productive beginnings and engineering judgment. And then I'll conclude by talking about some future work. Okay. So a bit about me. So as Robin said, I have my bachelor's degree from Michigan. So there's a picture of me in the Michigan marching band when I was an undergrad. So I was here for about 15 years ago. And then I went to MIT for my graduate degrees. So I have a master's and a PhD from MIT. I was a Draper Lab Fellow. And in my PhD research, I studied the human automation interaction. So looking at how human pilots interact with the autopilot. And so this is a picture here of me in the Draper Lab lunar landing simulator that I used as a part of my PhD. So as I really liked the idea of human automation interaction sort of conceptually or philosophically, and I think there's a lot of interesting discussion around that now with self-driving cars, but I just didn't feel satisfied by the research that I was doing. I didn't feel that I was really having the impact that I wanted to have. And so through some connections, I was able to get a postdoc at the Tufts University Center for Engineering Education and Outreach. And this is where I really started my career shift onto engineering education research. So I was at Tufts for about 2 years, and then I came back to Michigan to postdoc for Cindy Finelli. We were doing this flexible classroom project, and you can see one of the flexible classrooms there in the bottom right. I actually forget, I think that's a 133 Chrysler, if I'm not mistaken. So I postdoc with Cindy for 3 years. And for the last 2 years of that postdoc, I was also teaching Aero 215 here at Michigan. And then for the past 2 years, I've been an instructor out at the University of Colorado Boulder in the SMED Aerospace Engineering Sciences Department. And just started back at Michigan about 2 months ago, and very happy to be back here in Ann Arbor with the chance to do engineering education research in the department where I got my bachelor's degree. So I'm still getting set up. This is a picture of my lab space here, which I've done nothing to yet, but I'm calling my lab the Shuttle Lab for our focus on studies of holistic undergraduate thinking, teaching, and learning in engineering. And of course, the obvious aerospace connections to the space shuttle. So I'll invite you all back whenever my lab is renovated, probably next summer. So I want to talk a bit about my just general philosophy of research and how I approach engineering education research. And I like to think of it kind of as this ascending spiral. So research, engineering education research, I feel, has to start with a specific need in engineering education, right? So there's something that we need to discover, or particularly something that we want to change about the way we teach engineering. And that, of course, leads to a research plan. And in my work, I really see the educational practice and the research as tightly coupled. I've been describing it as symbiotic, which I'm not a huge fan. I think that sounds buzzwordy, but I do think that describes what I want to accomplish, right? It's that as we are fulfilling a need in engineering education, we're doing research, doing fundamental research on how students think and how students are doing engineering, and then that leads to better practice, which leads to more research, which leads to better practice. So I really think of it in this kind of ascending spiral where the research and the education are very tightly coupled. And I think that's another reason why I'm very excited to be here at Michigan and be in the aerospace engineering department, able to teach those engineering science courses that are the focus of my research. This is certainly one model. There are other models of research where that research and practice is more separate, but something that I'm really committed to is this tight coupling. And in the end, this leads to improved fundamental understanding of how students think and how they approach engineering, also leads to an improved engineering education. So this is the sort of the general philosophy with which I approach all of my engineering education research. Specifically, I'm motivated to bridge the gap between engineering practice and engineering education. And specifically, in terms of education, I'm interested in engineering science courses. So those are these 200 and 300 level non-lab, non-design courses. And this is generally where my teaching has been. So the problems that engineers solve are open-ended, they're ill-defined, they're also socio-technical, right? So the engineered systems have good and bad effects on society. But in these engineering science courses, we typically are giving students, textbook homework problems that are closed-ended. They're well-defined, right? So we're giving students systems that have already been simplified down to conform to the assumptions of a particular mathematical model that they just learned in class. In engineering science courses, we also often don't make a connection to the real world. If we do, it's superficial. So I want to be clear in that these problems are necessary, right? I'm not saying that we should remove all textbook problems and completely change the way these courses. I think these problems are necessary for giving students practice with mathematical problem solving, helping them to see how this new formula they learned can be applied. I certainly think those problems are necessary. I do think that they should be augmented with other assignments or problems or experiences that bridge this gap between engineering practice and engineering education. And I think that's done through a focus on professional engineering practices. And I'll talk more in a few slides about two of the specific practices that I study. So overarching research questions, things that motivate me, that sort of most of my body of work is trying to get towards using qualitative methods to understand how students engage in the productive beginnings of those professional practices. And so the term productive beginnings comes from the science education literature. And so here's a quote, we're talking about productive beginnings in science education. They define it as epistemic activity that is or can become scientific inquiry. So in engineering, we might say, it's epistemic activity that is or can become engineering practice. So I'm certainly not claiming that engineering students can exhibit the same behaviors or actions as practicing engineers. Of course not, because engineers have all of this expertise. So we're not looking for undergrads to do the exact same thing that practicing engineers do. But instead, I seek to create new definitions of how novice engineers engage in these professional practices, right? So they're doing something at the undergraduate level that is a beneficial practice. It is kind of the beginning stages of that end practice that they'll get to when they're an engineer and they're working and they have all that experience. So that's what I mean by productive beginnings. It's sort of in contrast to a school of thought that says novice engineers do this set of things that are bad, and engineers, experts do this set of practices that are good, right? It's more of a novice engineers or students do these things that are good and then lead to these other things that are good when done by experts. Then I'm also interested in how instructors' pedagogy and assignments can scaffold students' engagement in these productive beginnings, right? So that's that research and educational practice connection. But of course, we can't design good pedagogy and assignments without first understanding student thinking. So that's why really this engineering education research component of the work is really important. So specifically, some of the practices that I'm interested in, the first is engineering judgment, which is the development and use of mathematical models for design and analysis. Another practice that I'm interested in that I won't have a chance to talk about today is macroethics, or thinking about the broader societal context and implications of engineered systems. So I've done some work with this and planning on continuing the work. I'm happy to talk more offline about this. In terms of a professional teaching practices and pedagogy, I'm interested in specifically responsive teaching, which is just a particular form or a process of formative assessment through that instructors can use to respond to the disciplinary substance of student thinking, or to identify sort of ways that students are thinking about the productive beginnings of these professional practices and encourage it. This is another thing. I did some of this work when I was postdocing with Cindy, and even when I was back at Tufts, and hope to continue it in the future, but something else I won't have time to talk about today. So this is kind of the body of work or my plans, focused around professional practices. Another interest of mine is just in supporting working class students in engineering. I think there's a lot of aspects of people's identity through which they are marginalized by the educational system that we need to study and focus on and correct. I think in particular, working class students from who are of low socioeconomic status, are an under-researched area. And this is coming out of work that my friend, PhD student, Corey Bowen did when she was here at Michigan. She's now a postdoc at Cal State LA. I think she was on. So that's another sort of growing research area that I'm interested in. And I can talk more about any of those sort of offline, but today what I want to focus on is engineering judgment, which has been my main project for the past few years. So this research is done in a large team. I'm very lucky that I have a lot of great people to work with. Jess Swenson, who's a professor of engineering education at the University of Buffalo, is my co-PI on the project. And so we work very closely together, and she's actually been leading it. When I was an instructor at CU, I didn't have too much research time. So she's taken the main responsibility for leading it over the past few years. But I'm at Michigan. We have an instructor at Buffalo, Alice, also Emma Treadway, a Michigan grad at Trinity University, my former colleague, Catherine Wingate at CU Boulder, Ahoda Kodyashar from Tufts University, and then another Michigan grad, Jinwoo Lee from Cal State Fullerton. So all these people have participated in the project as instructors or instructor researchers, and we hope to add more next semester. So engineering judgment, what is it? Well, it is the use of mathematical models in design and analysis. So it's essentially how engineers use math and mathematical modeling. And this list of 8 practices comes from Julie Gainsbourg's work. She's a math education professor at Cal State Northridge, and she did an ethnographic study of structural engineers looking at how they used math in design and analysis. And she came up with this list of 8 practices. And I won't go through them now. You can see things like, number 2, making assumptions or simplifications, or number 6, overriding official building codes. This was something that she saw engineers doing. Or number 8, determining typical elements or conditions. So this is the list that came out of her ethnographic work. And really, in summary, what you see is that the core engineering practice as it relates to mathematical modeling is not the calculation of some final answer, like we have students doing in those textbook homework problems, but rather the core engineering practice is the modeling of the system. And that's kind of what the textbook does for students, right? It kind of models it for them, and then they have to find that final answer. And so, I read this paper when I was teaching here at Michigan, when I was teaching Aero 215, and I thought, yes, this is exactly, some of the practices that I should be teaching in my sophomore structures class. And so in order to get these into the class, I developed this new type of assignment, the open-ended modeling problem. So there are 4 principles of OEMP design. So these problems, these assignments, they're open-ended, meaning there's no correct answer. They're also set in a real-world context or involve a real-world object. So the one that I did at Michigan is using that airplane at the bottom left. That's the Nomad, which is actually in the lobby of the aerospace building here on campus. We've done other OEMPs since, or other instructors have, with the iWalk hands-free crutch, with a pool lift, and also just with a slide in Boulder. So essentially what we do is, I'll talk more about kind of the details of what students do, but we give students one of these real world systems and ask them to model it, such that they can apply the canonical math models that they learned in their engineering science courses. So just those standard formulas that everybody learns in their statics class. We wanted students to be able to apply, we designed these problems so that students can apply those formulas to these systems. The problem is these systems are complex, right? They haven't yet been fully simplified down and modeled. And so students have to do that. So they have to take this real world system and model it in such a way that they can apply those formulas. And in doing so, in doing that modeling, students are practicing engineering judgment, and they have a chance to employ engineering judgment. So over the past 7 semesters, OEMPs have been used in 14 different course offerings at 6 universities. So it's something that started here at Michigan, just me trying to make my course better, and has grown into a larger research project and a larger implementation project as well. We have a lot of data, lots of survey data showing that students like these, they want more of those, but I'm going to focus more on the research and the development of our framework today. So what do students do in an OAMP? So digging down a bit further, I'm going to focus on this one with the iWalk hands-free crutch. This is the sort of the theme that's been done the most, and I'll talk a lot about this in the data. So you can see a picture of the hands-free crutch on the left, and on the right is a sort of an already simplified diagram that's given to students. There's a lot more that they need to do with it that I'll talk about, but we have sort of at least turned it, made it 2-dimensional for them. So in the open-ended modeling problem, OEMP, students first create a free body diagram or an impulse momentum diagram by making numerous assumptions. So they have to think about, well, what are the forces acting on this crutch? Where are they located? What is the magnitude of those forces? They also have to make assumptions about the dimensions. And as well, the stance of gait, right? So as the person is walking, what sort of stance of that gait is putting the most weight on this crutch? So that's the first step. That's really the modeling step. Second, once they have that mathematical model, they need to calculate the properties required by some part of the system. So for the iWalk, they are choosing a material in diameter for member AB, which is the vertical member going from the person's knee to the ground. And there are other things that we can ask, other properties with different problems that we can ask students to calculate or determine. Lastly, students have to gauge if their answer is reasonable or not and reflect on the model output. So oftentimes students get a really small answer for sort of this part of the system they're asked to size. And I'll show you some quotes from students about that later. And that's not because they made a mistake or because they did math wrong. That's just a function of sort of the modeling and the simplifications that they had to do. So we asked them to think about that and say, is that reasonable? Is it not? What might have happened? So reflect on the output of their model and think about why it gave them what it did. So students do the OEMP individually, and then they do it again in a group. And we've had various degrees of group work, from just discussing it in one class with some peers to doing like a full out-of-class group assignment. And that's sort of where we've gotten to, where students will do this or a subset of the work once by themselves, and then they get together in a group. And that gives students a chance to discuss assumptions with each other, to argue in a productive way about their assumptions they made and the simplifications, and then come to a group consensus on kind of what is the best model. And best is certainly a subjective word, but what the group thinks is the best. And hopefully that's better than sort of any one individual model. Also, as a note, I mentioned the categories of engineering judgment, or the practices of engineering judgment. We don't teach students those. We never just show that list and say, this is engineering judgment and what you'll be doing. We do have instructors who sort of generally talk about the motivations for this work and how it is, extending the course concepts to practices that are more professional practices. So the instructors certainly motivate the OEMPs, but they don't explicitly go through the categories of engineering judgment for students. So hopefully that describes the need, the need that we're addressing in engineering education. Also talk a bit about the OEMPs, that initial activity. Now I want to focus on the research. So sort of what are we doing to understand student thinking as they complete these OEMPs? So 2 research questions that we focused on. The first is just, when given the opportunity, can undergraduate engineering students engage in engineering judgment, a practice rooted in expertise? The fact that I'm giving a whole presentation on this probably suggests that the answer is yes, and it is. But when we started out, right, we didn't know if students would be able to do this, right? I thought they would when I gave them the first OEMPs, but we didn't know if students would be able to engage in these practices because they are rooted in expertise. And so this was really the first research question that we had to address as a part of this project. And then we said, well, okay, if students can just, engage in the productive beginnings of engineering judgment, what does that look like? In what ways do they do that? And so, of course, as we've said many times, the way that undergraduate students exhibit the productive beginnings of engineering judgment, it's inherently different than practicing engineers. So we can't look for them to do the same thing. So what's needed is a new theoretical framework of how novice engineers or undergraduate students engage in the productive beginnings of engineering judgment. And so this is what we're doing through an interpretive research paradigm. So I'm going to get more into the methods now. The goal is to develop in interpretive research, the goal is to develop an understanding of how subjects make meaning of their social reality. So it's really different than a lot of the engineering research or quantitative research that's really looking to test a hypothesis or kind of seeking the truth that is, the one truth that is out there in the world. So in interpretive research, everyone experiences some reality differently, and you're looking to understand how those, your subjects experience that reality and how they make meaning of it. So interpretive research is used for building a theory from the data and not testing a theory as in quantitative research. And I want to be clear too, quantitative research is certainly valuable. I think there is absolutely a use and a place for it. But in order to answer the research questions that I have, we need to use qualitative research. We need to use interpretive research, right? It's really hard to give a survey if you don't even know the ways in which undergrad students exhibit engineering judgment, right? So we need to start with this qualitative interpretive research. So the knowledge that's produced from interpretive research is idiographic in nature, in that it emerges from the unique perspective of individuals and groups, right? So it does really come out of the people and the situations that you're studying. But the knowledge is transferable to and meaningful for other contexts, right? So we are going to be generating knowledge from studying students who are engaged in open-ended modeling problems. But the framework we develop, the goal is to designer methodology and designer analysis such that the framework that we produce is transferable to and meaningful for other contexts. Also in interpretive research, the researcher's perspective influences how they make sense of the data and therefore the results, right? So because you are interpreting how your subjects make meaning, the positionality and the perspective that the researcher brings does influence sort of the final results. And so it's important to keep that in mind. And so talking a bit about my positionality, as I am one of the people who's analyzing this data, I don't have any industry experience. I've had a few research-based internships a while ago, but I have never worked in industry. And that's something I'd like to change, maybe get a summer internship some year. But that's sort of my background. I have taught mechanics and materials 6 times at Michigan and CU Boulder. I developed the idea for OEMPs. I was the first implementer. I co-originated the research with Professor Svensson, and I've also helped instructors at other universities develop their own OEMPs. So I'm certainly coming more from the academic side of things. And that is just certainly right. That influences how I interpret the data. And we have a number of people who are looking at the data. And so it's not just my perspective. We have others who have different positionalities, but certainly with qualitative research, it's really important to describe the researcher's positionality. It's also good to do for quantitative research as well, for sure. Okay, so our research design. So we're generally using a constructivist grounded theory methodology. That's sort of the name for it. So in grounded theory, there's sort of a debate of, there's a question of, well, how much do you read before you start analyzing the data, right? And sort of in classical grounded theory from the late 70s, the idea is that you should have no knowledge of the literature, no knowledge of any existing theoretical frameworks. You should just come to the data and start looking at it and see what theory emerges from the data. But in constructivist grounded theory, which is more recent, there's this idea of a sensitizing concept. So Sharma describes it as, or says this about the idea of a sensitizing concept. In a grounded theory study, you put your sensitizing concepts and theoretical codes to work in the theoretical framework. These concepts and codes locate your manuscript in relevant disciplines and discourses. Sensitizing concepts account for your starting point. So our starting point is Gainsbourg framework of engineering judgment that I talked about earlier. And we were certainly aware of this. This is where we're situated in the existing work. And this framework of engineering judgment, it informed the OEMP design. And we have a whole paper, me and Jess from ASEE 2 years ago, talking about how we designed the first OEMPs. This framework of engineering judgment also influenced our interview questions and our data analysis as well. But we're still building a theory up from the data and not testing a specific hypothesis. We also employed triangulation. So we have participants from multiple universities who are doing multiple OEMPs on different topics. So if we just studied students in one of my courses, perhaps there's something about the way I teach or these students or Michigan that influences how students make meaning of the OEMPs and how they employ engineering judgment. And so by looking at students at multiple universities, we can see sort of, we'll start to see the same thing at all universities, or maybe a couple of universities, and that lets us know that sort of that behavior is not particular to that instructor or that course or that university. Okay, so the data we have is from retrospective interviews conducted by Jess. She did some of them in person, but most of them have been virtual, or just over Zoom. So there was a semi-structured protocol, and we had that to remain consistent between students. She has a set of questions that she wants to ask, but there is the opportunity for her to follow up, to sort of riff off of something students said, to ask questions about something they say, to learn more. So there is, flexibility in that interview protocol, although we do have specific questions that she asks students. Jess asks students how they solve the OEMPs. She just says, tell me about how you solved it. Describe your process when you were solving this. They often will bring their work and talk through it to her. So this is how it's a retrospective interview, because they finished solving the problem. It's at the end of the semester, and they're remembering what their process was with the help of their work. She also asked them, how did you know your model was complete enough, or how did you know your model was accurate enough? Asked them kind of also to, beyond thinking about how they solved it, to sort of assess what they did. It's important to note that Jess does not use the specific language of engineering judgment. She doesn't say, tell me how you engaged in this practice of engineering judgment or this practice. So we don't use that specific language. That's what we look for in the data analysis. So altogether, the data that we have for developing this framework comes from 21 interviews with students. They were at 3 universities, and they all completed an OEMP during their statics or their mechanics of materials course. So all university names are pseudonyms. So there's 4 from Blue University, 10 from Yellow University, and that's 2 groups of students from the same course, but 2 consecutive semesters, and then 7 from Maroon University. So a bit about coding the data, then this is it's a difficult thing to describe how we code. I mean, I think even our research team trying to teach undergrads how to code the data can be somewhat of a nebulous process. I found this meme on Twitter, and I think it exemplifies what it's like to talk about coding the data. So I don't know, maybe you won't understand if you haven't seen Schitt's Creek, but you should see that for other reasons unrelated to this research. But sorry, I have popped the chat up in front of, anyways, I'll keep going. Okay, so how do we code? Well, so, we have these interviews, we transcribe them, we have members of our research team looking through the data. So it could be me, it could be Jess, who did the interviews but doesn't teach in mechanics, or we also have undergrads at the University of Buffalo who are coding this. And so some of them have taken OEMPs and done them, as students. So two things that people have to decide when reading the transcripts. The first is which utterances, when are students talking about any practice of engineering judgment? And then when they, we've identified, say, this is an example of engineering judgment, the next question is, well, what type of engineering judgment is it? So then we make iterative passes through the data using the constant comparative procedure. So we're looking for instances of engineering judgment in the data. We're comparing it against the emergent theory, and we say, okay, how does this piece of data fit within the theory that we have? Does it fit? Do we need to change the theory? And we're very open to modifying the theory when necessary. So it's really this back and forth between the data and the theory, and then you're looking for more data to make sure you didn't miss anything, changing the theory, so on and so forth. And the eventual goal is to develop a framework that is useful for researchers and instructors. Right, we want there to be some use from this data. All right, so now I want to talk about the framework, and we have only lost a fifth of our audience in going through that methodology. So no, it's a lot, right? But in qualitative research especially, it's important to describe the methodology, right? Like if I just skip to this framework and just show you this framework, you're going to have questions about like, where did this come from? How did you derive this? How do I know that this is, that this has been rigorously developed, right? So in qualitative research, yeah, it takes a lot of time to go through the methodology, but it's really important to give you, the listener or the reader, sort of confidence that that there has been some rigor and some quality when this has been developed. We could probably stand to do more of that for quantitative research as well. But the framework, so let's go through it. So these are the ways in which we see students exhibiting the productive beginnings of engineering judgment. So the first is by making assumptions or simplifications to be the bases of mathematical models. And so sometimes students tell us about assumptions they made and they don't justify it. I mean, presumably they had some justification when they made that assumption, while solving the problem, but it just doesn't come out in the retrospective interview. Then we do hear some specific justification. So sometimes students say they make the assumption because it made the model more realistic or accurate, representative, or typical. So we see students, going out to the Nomad aircraft in the lobby of the FXB and measuring it, or strapping the iWalk to their leg and walking around to try to determine which phase of gait puts the most weight on it. So things like that, trying to make assumptions to make the model more realistic. I will note, we never told them to make a realistic model. Students just choose to do that themselves. Sometimes we see students making assumptions that consider the user, the client, or the manufacturer. So one of the things we ask them with the iWalk is to choose a material. And we see students saying things like, I chose aluminum because it's light and that's good for the user, or it's easy to manufacture, or it's inexpensive. Also not something we ask them to do, but we see them doing this on the OEMPs. It's probably an influence of the first year design courses, where they do have to specifically think of a client or a user. And so they're sort of bringing that into our OEMPs to help them make decisions. So two assumptions that are similar. So sometimes students make assumptions that have to make assumptions so that the model becomes solvable. And sometimes they make assumptions to make the model easier to solve. So a bit more about the difference between those. So I'll talk about two quotes from Lane, who was a student at Maroon University. And so on the left, you can see the free body diagram of the IWalk. And so discussing an assumption she made to make the model easier to solve, Lane said, I approached it as simply as possible, like putting the weight directly over the leg member AB and trying to simplify those forces as much as possible to be able to use the tools that I had just learned. So Lane is thinking about where to put the weight of the person on this free body diagram. And oops, sorry, I exited out. Okay, can you see it again? Looks like you can. If somebody could type in the chat like, oh, I can see it now, that would be good. Okay, cool. Thanks, Rob. Yeah, so my goodness. Sorry. I'm gonna bring it back up again. I just stopped my screen share. You can tell that I'm not teaching this semester because I've forgotten how to use Zoom. Okay, are we good? Okay, I'm going to assume that you can see this. If you can't see this, just type in the chat. What are you doing? Please put it back. All right. Okay, good. All right, let's get back to it. Okay, so we're talking about Lane's assumption that she made to make this problem easier to solve. So she put the weight force of the person right at point B. Now, she could have put this anywhere along that member EC, and she still would have been able to solve the problem. But she said, well, I know it's going to be easier if I put it here. It makes the math a bit easier. But then another thing we asked students in this OEMP was about the nature of joint B. So it could be a pin joint, meaning it would rotate, right? As sort of the whole system could rotate about that point, or it could be a welded joint where it was fixed in place and it would keep that right angle between member AB and CE. So we gave students the option. And what sort of happens is if you make it a welded joint, most of the time the problem is unsolvable, right? You have to make a bunch of other assumptions in order for it to be unsolvable. So you make the welded joint, students were often running into a situation where they wouldn't be able to solve the problem. And Lane notes this when she's sort of initially thinking about it. She says, I went ahead and chose a pin joint for joint B because of the way I had modeled the members and the forces. The pin joint made it statically determinate, which just essentially means solvable at this sophomore level. The pin joint made it statically determinate and allowed me to be able to just kind of be able to solve for everything. So that's the difference between these two practices, right? Putting the weight at that point makes it easier to solve, but she could have put the weight elsewhere and still been able to solve it. But making joint B a pin joint makes it solvable, and otherwise it would be unsolvable with the knowledge that she has as a sophomore engineering student. Okay. So we also see students making assumptions because they think those assumptions won't impact the output of the model. So students, one student said, I'm going to ignore the weight of all the IWalk members because I think that's negligible compared to like the force of the person on top of it. We also see students making assumptions to model what they think is the worst case scenario, which is something, we asked them to consider when sizing member AB. Sometimes students just make assumptions based on their intuition. So they just say, that just feels right to me. So these are sort of all the justifications we've found so far for students making assumptions. I should note as well, I should have said this earlier, we are still in the data analysis. We've gone through the transcripts a lot, but Jess has some new undergrads who are starting over, looking at the transcripts from scratch to see if they find new utterances of engineering judgment or if we can modify the framework more, right? So essentially you just want to, in this interpretive research, you just want to go through the data until no new theory emerges. And I think we're getting to the end of that, but we still have those two undergrads going through it more. So if you see our published work on this and the framework is a bit different, that's because we're still in the midst of this analysis. So another sort of category of engineering judgment practices we see is assessing, right? So we see students assessing a few things. One is the assumptions that they made. So here's a student from Blue University who said, I assumed that joint B was fixed initially because it seemed more realistic, and I realized it would be harder to solve if it was fixed. because there would be an extra moment that would have been fixed. And as we said, in reality, it's unsolvable if um, often if joint B is fixed. So this student, they made that assumption, then they kept going along with the problem, and then they got to a point where the math wasn't working out or it's complicated, and they said, I need to go back and reassess that assumption that I made. So this is something we see students doing. Students also assess the output of their model. So as I said earlier, students often get a small answer for their diameter, and it's just a function of sort of the problem and the assumptions they have to make. And so Lane reflected on that. She said, we got a diameter about a 1/20th of an inch. So we knew it would support this load at 1/20th of an inch. Essentially, the math is saying that it would support that is an okay diameter. But we didn't really think that was the best diameter, again, because of the balance issues. So she thinks, it's going to be really hard to balance on a support that is 1/20th of an inch in diameter. So Lane and her group members are assessing the output of the model. I want to jump ahead to sort of practice number 4 because it relates to this. So in some cases, we saw students overriding their answer and deciding to override the answer that they got. So Lane quotes continue, she says, so then we went ahead and kind of assumed and chose a radius of a 1/2 inch, so a diameter of 1 inch, which is kind of knowing it would support that. We just kind of made the diameter bigger so that it would be more reliable and be more protective when actually walking. So the math, the output of the model says that the answer is 1/20th of an inch. And some students just wrote that down and said, sure, I'm going to make this member 1/20th of an inch. It seems weird, but that's what the math says. Whereas some students, like Lane, said, that doesn't sit right with me. I'm going to make the diameter bigger so we have, so it's more reliable, so there's some margin. So they chose to override the answer that came from their mathematical model. So the last thing that students can assess is the model as provided by the instructor in the problem, right? Sort of, we do keep these systems open-ended. There is still a lot of assumption making and simplifications that students have to make, but just by virtue of assigning this as a problem in a sophomore course, the instructors, we have to start by making some simplifications already. Otherwise, the students couldn't even get started, right? And so some students know that and they reflect on that. So here's a quote from Christina at Maroon University. And she's, the way that students were given the OEMP at Maroon University is they were it was in 2 parts. The first part was just to look at the entire iWalk kind of as one monolithic system. So as you can see in the picture, they're kind of all those bars fixed together. And then in the second part, they essentially took it apart and looked at the internal forces and the reactions between the different bars. So Christina was saying the very first assignment, we didn't include all the individual things. And so I felt like it was weird because once I turned it in, I was like, I don't feel like it's the best it could have been because it didn't include like real life things like the internal forces and things like that. So Christina is reflecting on sort of the model as provided by the instructor in the problem and saying, well, it seems incomplete or it seems like it's oversimplified or missing a lot of things. So we see students assessing that kind of the initial model that they're given in the problem. Then lastly, we see students deciding how to use a technology tool to help with analysis or computation. So students have said like they chose to use CAD to model the iWalk and look at the dimensions of it and think about the forces. Or one student had a diagram of the iWalk and was counting pixels on his computer screen to tell how to figure out the dimensions. So we see students using their judgment to decide on how technology can help them to solve this problem. And then the fourth kind of category or fourth practice already talked about. So here is the full list as it stands now. As I said, we're still sort of going through it, looking through the data, just making sure that we reach that theoretical saturation and that we have this framework and nothing new is going to come out of the data. And so we are working on publishing this. I'll just bring this up. I messed up my animations on this slide, but to go back to our research question. So when given the opportunity, can undergraduate engineering students engage in engineering judgment? Yes, they can. We definitely see evidence of that. And then And so they can. So in what ways do undergraduate engineering students engage in these practices? This is what's captured in the theoretical framework of the productive beginnings of engineering judgment that was on the previous page. And we see that there are similarities and differences to engineering judgment as exhibited by practicing engineers, which we certainly expected, right? There are some similarities. Both students and practicing engineers have to make assumptions and simplifications. They also have to assess their assumptions. But like we see students making assumptions to so that the problem is solvable. That's not something that practicing engineers necessarily do, right? Practicing engineers make assumptions to make the model easier to solve, certainly, but they can use more complicated tools or more complicated analyses to get over that hurdle of, if they run into an unsolvable problem, they can use techniques that are able to solve that. Whereas sophomore students, sort of there's a limit to their knowledge, and so they run into a point where the model is unsolvable. So we do see similarities and we do see differences. So what are the implications for practice? Well, we think instructors should include more open-ended real-world problems in engineering science courses. We're certainly supporting instructors in implementing OEMPs, but I think any type of open-ended problem is great and beneficial in addition to those textbook problems. It's also important to note that there's some progression through the curriculum, right? So the first time students see an OEMP, there's like a big hurdle just understanding what we're asking for in some ways, because they're so used to these textbook problems that they get these OEMPs and they say, well, what's their answer? And then you as the instructor say, oh, there's a bunch of answers. You just have to justify your answer. And they go, no, but like, what answer do you want? And it's like, well, there's a whole bunch of them. So it just takes some time for students to understand how to grapple with that open-endedness. And so we've seen students, the next time they do the OAMP, they're more comfortable in that open-endedness, and they also have more expertise. So, they need less scaffolding and can engage more in engineering judgment for the productive beginnings of it. Also, I think it's important for instructors to specifically name and encourage the productive beginnings of engineering judgment. So tell a student, you're doing this, and that is a productive beginning of something that practicing engineers do. And we do see students, they tell us that these problems make them feel like a real engineer. And sort of overcoming initial frustrations, that's a body of work that Jess is pursuing with these problems. But it's important for instructors to name those behaviors and point them out. Engineering judgment inherently occurs in design classes, so it's also productive to emphasize how that occurs and those connections between design and engineering science courses. So our future work in this direction is to complete the theoretical framework and to publish it. Hopefully we'll submit it soon, so look for it in print in a few years, I guess. We also have additional data we want to collect. So we have interviews with students who completed a dynamics OEMP. We also have group discourse from 2 schools. So as students are collaboratively, completing an OEMP and discussing and arguing with each other about their assumptions. So that's a big set of data that we have yet to analyze. And I think that'll be really interesting and a really interesting sort of comparison complement to the retrospective interviews. We also want to iterate on dynamics OEMP. So we've done some, but we're forming a group of 4 instructors who will implement them next year, sort of work collaboratively to design and implement them. So that's some work we're spinning up. And then also disseminating OEMP assignments and guidelines. So sort of another aspect of my future work in a related direction is thinking about this continuum, right? So we've there's literature on engineering judgment and professional practice. And with these OEMPs in this work, we've looked at engineering judgment in introductory mechanics courses, sort of that framework for the productive beginnings. And it's a continuum of development, right? And I'm really interested in kind of the middle here. So what does that look like? And I think a great place to look at that is through experiential learning and senior design. And this ties in well, I think, with the Immerse program here at Michigan. Because students that are on project teams or in senior projects, they have more expertise. They've been through their education. Also, their tasks are inherently open-ended, right? If they're designing a rocket or a human-powered submarine, or something like that. It's an inherently open-ended and ill-defined task, but smaller in scope and scale than a professional engineering task. So some of the research questions I want to address, in what ways do student project team members engage in the productive beginnings of engineering judgment when using those canonical models from their engineering science courses and when using professional engineering software? That's a big part of student project teamwork. And so I want to look at how students use that software and interpret and understand and trust their results. How do team members develop and pass on knowledge in engineering judgment? How do team members talk about that knowledge in engineering judgment to employers, when they're putting together the resume or on an interview? And really sort of a main motivation is how we can use this fundamental knowledge to improve engineering science courses. It's great that students in project teams are in these experiential learning co-curricular activities have these beneficial experiences, but not all students can engage in project teams because maybe they need to work or they are living at home or other reasons, right? So I think, we can't certainly replicate a project team experience in an engineering science course, certainly not. But I think there's some things that we can replicate, right? And give students some of those experiences to improve our engineering science courses and help them to engage in the productive beginnings of engineering judgment. So that's it. Thank you. I think we have some time for questions now, and I put a picture of my children there, so you feel bad if you ask me a tough question. But I mean, in reality, so one of the things I started doing during the pandemic is really letting students know that I am a human and encouraging them to do things outside of engineering. The past few years, everyone's mental health has been poor, including myself, and it's incredibly important for students to get outside and do things that aren't engineering. And so, I try to practice what I preach and try to tell students about the things that I do. And I think while I'm reintroducing myself, to you all, I think that's good to make note. So, I do have two kids, Lillian and Liam. We like to hike. That's I'm from out in Colorado. I like to play disc golf, bike, collect NASA Lego. I have a large collection that will be set up in my office soon. And I put the top left picture in preparation for our game against Michigan State in a week and a half. Oh, and I'm actually in the background of this picture from when I was an undergrad. So I will take questions now. I see, I have a question in the chat or in the Q&A. I will take that. You can put more questions in the Q&A or in the chat. So the question in the Q&A says, do the instructors review the idea of overriding the answer? Basically, is there a way for students to practice if this intuition is appropriate or not? That is a good question. I mean, the instructors certainly review what students submit, and you do have to grade these, right? They are part of class, so you do have to grade them. In general, we grade more for justifications, more for the right answers. So I would say if a student had a good justification for overriding the answer, then they would get credit for it, and the instructors would review that. Another thing, and if they made like a bad overwriting, if they didn't justify it well, a point would be taken off. But I will say one of the things that helps in understanding when to override the answer is having a real world object that students understand, right? So like I've used the Nomad aircraft in the lobby or the iWalk. Students can go out and look at the Nomad in the lobby, or they can look up the specs for the iWalk, or one instructor bought an iWalk for students to have and look at and try out. And so that grounds students, and it helps them to assess the reasonableness of their answer. And we have a full paper on this from Frontiers in Education next year. I'm trying to think how far back it is. How far do I have to? I don't want to go back through all the. Where? No, I've committed to this. Okay, is this? Hopefully you can see my screen. It's Swenson, Johnson, Roland, Suzuki. So we looked at how students assess the reasonableness of their answers. And what we see is that they compare it to the actual object, right? So if they're getting a diameter of 1/20th of an inch, they can look at the iWalk or look up the specs and see that it's greater than 1/20th of an inch. Or, they can go out and compare their answer to the landing gear of the Nomad. And so that gives them a way to assess whether or not kind of their intuition is appropriate, right? And so, but the first time I did it, we did it with a hypothetical bridge. And I think that was a bit harder because to assess their answer. I mean, we had students getting like cabled, they had to size these cables and they got answers of like 8 feet, right? And like, I don't even think like the Golden Gate Bridge has cables with an 8-foot diameter, right? So like, if it's extreme cases like that, you can kind of intuit whether that's reasonable or not physically, but having something real world and tangible is really helpful. All right, any other questions?
In the chat, Aaron, you have a comment that I think is kind of a little bit of a question too from Nagash asking about, like, it seems like they're also developing engineering identity. Can you speak to that?
Yeah, definitely. So I do think that they're doing that, right? So this is a lot of the work that Jess is continuing it on, looking at epistemic affect. And we actually have a paper from the Frontiers in Education conference last week, looking at how students, develop sort of affect as relates to their thinking and their doing of engineering. And we definitely see that, right? So students, they look at these problems, they say, they make me feel like an engineer. They sort of recognize that these problems look more like engineering problems than the problems that they're used to solving or the problems that they expected to solve in the course. And it does, they do say things like, it made me feel like an engineer. Or it makes them, they become more confident as through the process of doing them. So, we do see that, and that's a line of research that Jess is pursuing. We haven't specifically looked at like engineering identity, but I would guess that it is making them developing that identity. I sort of see another motivation for doing this, right, is I think we get students who come in their first year and they get all excited with like Engine 100, right? And they're like, this is what I want to do. This is why I became an engineer. And then we get to junior, it's like, now do all this math. And right, it's like a lot of math that's pretty divorced from context and devoid of context. And so I think there can be a shock where they're like, oh my goodness, this isn't what I wanted to do. And all that is important for engineering. And I think it's helpful to connect all that math and mathematical modeling to the practice of engineering. And so I think that can also help with engineering